Before we begin taking notes on section 6.3, please make sure that you have printed out the PowerPoint so that you can copy down everything that you need as we go through the PowerPoint slides. Now, our goal today for this section is to make sure that we can solve an exponential equation, which looks something like the example we have here. This would be our simplest one, where the variable is up in the exponent, and it's pretty hard to use mental arithmetic to figure out the value of x. 7 to what power gives us 12? One we might be able to do in our head would be something along the lines of 3 to the x equals 9. Well, you can think, 3 to what power gives us 9? Pretty quickly, you'd be able to find x equals 2. And that's because both 3 and 9 have the same base. So 3 to the x equals 3 squared. X has to equal 2. You might also know that 3 squared is 9, just naturally. But this is a thought that we may have explored in one of our previous sections. On the other hand, 7 and 12 have absolutely nothing in common in terms of the base. So we need to use a property of logarithms to be able to take the x out of the exponent. This is called the power rule. So we can take either the natural log or the logarithm of both sides. And then the exponent can be brought down in front as one of our properties of logarithms, so that I could write this as a multiplication, and then if x is multiplying, I just need to divide. Oops, but it helps if you divide by the right number. So the exact answer is that x equals the ln of 12 divided by the ln of 7. If this doesn't tell us to round to any particular number of decimals, but when you're working with exponential and logarithmic problems, they usually want at least 4 decimal places. So using a calculator, if I were to try to evaluate this to 4 decimal places, I would come up with 1 point with a little bit of rounding involved, just to give you an idea of how large or small the ln of 12 divided by the ln of 7 is. Now, as we work through some of the next couple problems, our goal is to get our exponent all by itself. We may have to subtract, we may have to divide, but we want that, like the 7x, that part has to be alone. We need to isolate that. And then we have the little part about getting the same base, if possible, or we take the ln of both sides, like I did in the previous example. Now, on your paper, these problems should look a whole lot nicer than what I have here. And so let's see if I can read this. It's not 23x in our first problem. It's actually 2 to the 3x equals 16 to the 1 minus x. Now, if I look at our bases here with 2 and 16, I can actually take 16 and put that as a power of 2. So that's my first step. 16 is, I think, 2 to the 4th. So let's see what happens when I do that, how is that going to impact the rest of my 1 minus x? Well, 1 minus x is then being raised to 2 to the 4th. So the 4 and the 1 minus x would be multiplied together. And since I have the same base of 2, I can now set my two equations equal to each other. And this equation is now much easier to solve. I'm going to bring the 4 over, divide both sides by -4, oops, I lost an x as I was working through here. So let's try collecting like terms together. Okay, so this time I will add the 4x, so I'll have 7x over there equals 4. So x equals 4/7. There we go. If we take a look at the next problem, and let me see what this is. 3 is raised to the -0.1, and the variable is t, but I'm going to change that to the variable x just because t's and addition signs kind of look the same. The way that this is set up is going to become quite familiar to us as we continue working in some of our word problems. And my goal here is to isolate the exponential part, what's in the parentheses. So I need to get the 1,000 out of the picture. I'll divide both sides by 1,000, and that means I now have 2 equals my base. And there is no way that I can have 2 and 3 have the same base the way I did with my 2 and 16. So here's an example where I would take the ln of both sides to be able to bring the exponent of -0.1x out in front. And now I know the ln of 3 is some random number, big long decimal, and I know -0.1 is also some interesting number. So I'm going to take the ln of 2 and divide it by all those coefficients that I had on x. So this lovely fraction here is my exact answer, and I could approximate that by using a calculator. And putting the entire denominator in parentheses. And getting a lovely answer. Now this is saying check your answer graphically using a calculator. So I'm supposed to check on a graphing calculator to see if you know, the two sides of the equation are actually intersecting where we find x equals. So let's try one of them. Maybe the first one. We'd have to use our graphing calculator and see if we can find where they intersect. I'd have to graph each side as a separate y equals. So for instance, if we wanted to check the first one, I would have y1 equals 2 to the 3x, and I would have y2 as 16 to the 1 minus x up as my exponent. And then I'm going to try to graph the two of those on the same screen. And I can see that those two exponential graphs do intersect in the viewing screen that I'm looking at. Somewhere, you know, it's nice and positive. And so I'm going to do a second calc, and then number 5 is for intersection. And there's a first curve and a second curve and a guess that I don't care about. And it says x equals 0.5714, so this is my intersection. Okay, which does not look like 4/7. So now I'm going to go check out what is 4 divided by 7. Okay, well 4/7 equals 0.571428511714. Would you look at that? Pretty close to the same answer, wouldn't you say? Imagine that. Now on the last slide we looked at the first two examples. Question number 3 is exactly like what we did in question number 2, I think. Maybe not, so never mind. Let's take a look at question number 3. I know that I have 9 times 3 to the x, and I'm looking at the number 72. Oh, no, I'm looking at 7 raised to the 2x. Now, my right-hand side is base 7, but my left-hand side has 9 and 3 to the x. So I can't just divide both sides by 9 the way I did in question number 2. So I need to do something with the 9 and the base 3. And if we recognize that 9 is really 3 squared, which I think we all do, I now have the same base of 3, and I have a squared and an x. So if we have the same base, and we're multiplying the bases, we can rewrite that as adding the exponents. And now I have a similar situation to that 7 to the x equals 12. I have completely different bases. I have exponents up high. I need to take the ln of both sides and bring my exponents down in front. So I have x plus 2 ln of 3 equals 2x ln of 7. And now I need to get all the x's on one side and all of the numbers on the other. So as I was saying, I have x ln of 3 plus 2 ln of 3 equals 2x ln 7. And now I need all the x's together. I need the numbers on the other side. So at this point, it's really just an algebra problem trying to get the x's on one side, the numbers on the other side. And although ln of 3 or ln of 7 looks like a variable, it's some big long decimal. So let's see what we can do here. 2 ln 3 equals 2x ln 7 minus x ln 3. So I have an x here, and I have an x there, and we're going to use our fabulous factoring capabilities to factor out an x. So I would have 2 ln of 7 minus the ln of 3. And to get that x all by itself, right now it's being multiplied by everything in the parentheses. So to undo multiplication, I'm going to divide. And if I divide on one side, I need to divide on the other. So this beautiful fraction that we have is the exact answer for what x equals, which, not knowing too much about the values of ln of 3 or the ln of 7, much less multiplying by 2 and subtracting some of them, may not give you a really realistic picture of that value. So if we approximate this on our calculators, using a lot of parentheses, we get about 0.7866. So at least we have some idea that it's, between 1 and 2. And the rest of our problems are in a similar vein of trying to get all the ln's on one side, all the x's on the other, isolating the exponent or the exponential part, and we take it from there. Now in these problems, we're not quite being asked to solve anymore. We are being asked to figure out where our exponential equation is greater than or equal to 0. The flip side of that would be where our exponential equation is less than or equal to 0. We will need a sign chart. At some point in this process. So let's see what we can do along the way, and then use the sign chart to find out where this right now inequality, but down the road equation, is positive, and then what happens. So right now, I happen to notice that we have a base 4 and that we have a base 2. And I'm betting that we can change into all of the same base, and that's going to help us use or solve this problem. So base 4, I can write as 2 squared which I could then change for purposes of solving this as to 2 squared equals 2. So I brought the 2 over and I changed it from a greater than or equal to sign into equals so that this helps me solve it. 2 has an exponent of 1. I have the same base, so I can then write the equation and solve for x. So that looks like 2x minus 4 equals 1. Bring the 4 over, so 2x equals 5, x equals 5/2. And now I need to go back to create a sign chart with my 5/2. And I need to test, where is this positive or negative? Now, when we're using our sign chart, I need to plug in values bigger than 5/2 and smaller than 5/2, maybe the number 3 and maybe the number 0. I am plugging these test values, 0 and 3, back into my exponential equation, and I'm checking to see if my value is positive or negative. So when I plug in 3, I got a positive value. When I plugged in 0, I got a negative value. And so as I'm writing out in interval notation the results, I only want the positives. So I would say that this exponential inequality is positive on the interval from 5/2 to infinity. And I'm including 5/2 because it could be 0 at that spot. Now, the second problem that we have here, I recognize that 16 is also a power of 2. So I have 2x squared minus 3 equals 2 to the 4th. And so I'm just going to start this right away as x squared minus 3 equals 3x. Bring the 4 over. X squared minus 3x minus 4 equals 0. Look for factors of 4 that add to negative 3. So I think x minus 4 and x minus 1. X plus 1, there we go, equal to 0. So x equals 4, x equals negative 1. Those are going to be the values that go into my sign chart. And so I'm going to pick some test points, maybe -2, 0, and 5. And I'm going to plug those values in to my exponent, checking where I get positive results and where I get negative results. And so when I plug in 0, that's the easiest one, I am going to get 2 to the 0, that's called 1, minus 16, that's certainly negative. When I plug in 5, I get a really big number, and that's got to be positive. And when I plug in -2, that has to be positive because I'm subtracting off a negative, like a negative gives me a positive. That has to be positive. So if I am looking for the intervals that are positive here, I would be going from -infinity to -1, and I'm going to include that because I have a greater than or equal to, together with the interval from 4 to infinity. Okay, so we've seen this coffee example in one of our previous days working with exponential information, and so our function is the same, that 70 degrees is room temperature, and then we have we have our coffee cooling down. That's why we have a decay, according to, however long it takes. And we want to know when it happens that the coffee is going to be warmer than 100 degrees. And our C here is for coffee, not Celsius. So if you do all this work, we get a value of 10 ln 3. That would be the exact temperature. And if you look at this graph, we have an intersection here where we're looking at the 100-degree mark and our curve of our exponential equation, and our sign chart is helping us fill out when our graph is above the 100-degree mark and when it's below the 100-degree mark. And so we obviously want the numbers that are positive, that are warmer than 100 degrees Fahrenheit. So from time 0, and that's going to be up to ln, nope, to 10 ln 3. And this just says warmer. It doesn't say that it's at 100 degrees Fahrenheit, so we need parentheses, not a bracket.